All right, so the last topic we're going to talk about is energy as it relates to vibrations. And what is really interesting is that we can actually use energy methods to get the equations of motion. And this is especially easy if you have like a lot of moving parts, like maybe one piece that's attached to another piece and you don't want to go through all the trouble of separate free body diagrams. You can use energy. So, yeah. Here, and the trick, the basic math we're going to use is we're going to take the time derivative of the sum of the kinetic and potential energy. So, and this is essentially if you have an undamped system, whatever energy moves from the potential energy of the spring, it goes into the kinetic energy. So the energy is just essentially transferring back and forth between how the mass moves and how the spring is compressed. So when the spring is not compressed, the mass has a lot of kinetic energy and vice versa. All right, so, and I like this at the end of the class also because we get to kind of do a little review about these energy terms. So we're going to have our kinetic energy is going to be equal to 1/2 mv squared, and remember we're taking the v about the center of mass, plus our 1/2 I bar omega squared, and remember this is the I bar about the center of mass, and that's going to equal our kinetic energy. If there was a fixed point, then we could take I omega about that fixed point. We could take the moment of inertia about that fixed point, and then we wouldn't need this term. But so it depends on which way the problem goes easier. And remember, we're summing this. If there's more than one mass involved, we're going to be summing this. So then we also have the potential energy where we're going to have the sum of all of our mgh, and remember h is h bar, so it's the height of the center of mass, plus any springs we have here. So we've got our 1/2 kx squared. All right. Now, this assumes no damping, so if there are ways of handling damping in energy problems, but we're not going to do that here. We're going to assume that there's no energy loss to damping, and none of the damping terms are represented in these expressions. All right, so let's do like a quick example, just to sort of convince ourselves that this is working. So here we have our spring and our mass hanging from it, and we're going to define some displacement x from the equilibrium position. And so we're going to have our change in our kinetic energy, 1/2 mx dot squared, plus our change in our spring energy, 1/2 kx squared. And we know that the rate of change of all of that is going to be 0. So all we have to do is take the derivative of these terms. And so when we take the derivative of x dot squared, we're going to get our x dot times 2, which is going to cancel out this 2, and we're also going to get this x double dot term. And then when we take the derivative of this, we're going to do the same thing. We're going to get our x and then times 2, which will cancel this one out, plus our x dot term. And then this will happen every time. This will be how you know it's working right. The single dot terms will cancel out, and you'll have, just like we had before, mx double dot plus kx equals 0 for our simple base system. All right, but let's do this on another problem where we can kind of show when this becomes a little bit more fun. All right, so what if you had this like rolling wheel, and the wheel is light, the hoop is light, but all the mass is in this rod. And if we kind of redraw this, you can see that the length of the rod is equal to the radius of the wheel. And so like the types of oscillations it's going to have are the starting out here and then rolling up to one side. All right, so we have our kinetic energy terms, and that's going to be a 1/2 I. And now I chose I about the ground because this is a fixed point here. And I knew that with a little bit of isosceles triangle geometry here, we could convince ourselves that the distance between the ground and the center point is always going to be L over 2. So, and that's based on the argument that, you know, we have some isosceles, we want to use the parallel axis parallel axis theorem between the center of mass, which is always L over 2 away from the center, and the fixed point, which is going to be the ground. That's always where the velocity is 0 at that instant. And then, so we know that this is L over 2, and we know that this angle here is going to be the same as this angle. And so when that's true, we have an isosceles triangle, so this length is the same as that length. All right, and so then if we put that in here, we've got our parallel our moment of inertia about the center of mass, which is 1/12 ml squared, plus our parallel axis theorem term, which is ml over 2 squared. So that's just the distance times the distance squared times the mass. Substituting this in here and simplifying these terms, we're going to get 1/6 ml squared theta dot 2. So let's keep going. And now, and so now we're going to take the derivative of this, and we're going to get a theta double dot term and a theta dot term, and this 1/6, we're going to take that 2 down, so it becomes 1/3. All right, and now for the potential energy, we can think of the height as being from the center of our circle. So we can think of it as kind of going in the negative direction. And then we could measure that by saying that it's going to be as high as the cosine of L over 2 down, and we've got our mg term. And now we don't want to make our small angle approximation yet. This is a key place where you could make a mistake. And you don't want to just assume that this is 1, because then you're assuming that the height doesn't actually change. And we know that this is essentially like a pendulum problem, so we want to make sure that we're dealing with our gravity terms here correctly. So we're going to keep that cosine in there and then take the derivative to get this sine term, and then we're going to make our small angle approximation. So here we've got our mg L over 2 sine theta dot equals, is approximately equal to mg L over 2 theta dot. And now when we put these together, we're going to add our change in potential energy with respect to time plus our change in kinetic energy with respect to time. And now a bunch of these terms cancel. The mass, one of the lengths. And so then we would have it in the same typical form that we always have, so we can calculate the natural frequency as the equivalent stiffness over the equivalent mass. And then that would, when we square this, we don't have the square root, but then, so now we've got it again over here. And remember, just remember again, that natural frequencies are always going to be in radians per second. And then your period is always going to be, you want seconds per cycle, right? So we're going to use 2 pi over the natural frequency to get the right answer. Just one more note on this problem is, let me kind of zoom out for the whole sheet, is that we always want to be expressing our potential energy and our kinetic energy in terms of some state variable, in this case theta, right? And that's the variable that's changing during the oscillations. So that's how we know we're kind of putting our kinetic and potential energy in correctly, because they're all in terms of that theta.